Every large-scale retail operation relies on a fleet of wire baskets and middle frames to move goods from the shelf to the checkout. The shopping cart facilitates the vast majority of supermarket transactions, functioning as a critical component of the store's physical infrastructure. The design of these vehicles reflects a balance between consumer psychology and fleet management logistics. Every weld and angle is calculated to handle high-volume use while remaining navigable for the shopper. Maintaining this infrastructure requires significant scale. A single large grocery location often maintains hundreds of vehicles, representing an upfront capital investment that can exceed $50,000. For this investment to be profitable, retailers must successfully offset the costs of maintenance and security with the volume of revenue these carts drive into the store. Early grocers faced a consistent revenue ceiling. Shoppers stopped adding items to their handheld baskets once they became too heavy to carry comfortably. In 1937, Sylvan Goldman removed this physical constraint. He adapted the mechanics of a folding chair, added wheels, and placed wire baskets on top, mobilizing the shopper's load and allowing them to carry more than their own weight. Removing that physical burden allowed stores to expand floor space, stock heavier bulk items, and introduce larger packaged goods. Mobilizing the basket changed grocery shopping from a rapid, limited errand into a high-volume purchasing routine that could last for an hour or more. Modern cart dimensions leverage a behavioral concept known as the emptiness effect. This 3D visualization illustrates research by Martin Lindstrom. Expanding a standard cart to double its physical size correlates with a 40% increase in goods purchased. Abundant empty space suggests the trip is incomplete, prompting shoppers to keep adding items until the basket appears full. Physical capacity is paired with ergonomics. Features like fold-out child seats, convenient cup holders, and smartphone mounts keep shoppers comfortable and lingering longer. Retailers also tailor specific models for different demographics. This includes motorized vehicles for mobility assistance and smaller hybrid carts designed for quick midweek shopping trips. Prolonged engagement with the cart presents a secondary revenue stream. Stores regularly monetize the equipment by selling advertising space on the push handles or front-facing panels. Every inch of physical volume and ergonomic design removes friction from the shopping experience and increases the average transaction value per visit. Sustaining this complex system requires rigorous engineering. Manufacturers assemble kilometers of steel wire and specialized plastic components to withstand constant daily impacts and weather exposure. Once deployed, stores face the spatial challenge of storing hundreds of these large vehicles at the main entrance without blocking customer access. These modern black metal carts utilize a tapered geometric design. This enables nesting, allowing them to slide together and severely compress their physical footprint. Maintaining this orderly supply requires continuous labor. Store employees must consistently retrieve dispersed carts from parking lot stations to ensure an adequate supply remains during peak hours. Regular maintenance on the wheels is an operational requirement. A jammed, vibrating, or noisy caster can frustrate a customer enough to end their trip early. To maximize revenue potential, the supermarket must operate as a constantly moving micro-fleet management hub. Maintaining the fleet combats an $800 million annual global loss. These abandoned carts represent stranded capital assets, permanently removed from the retail environment. To combat this, stores deploy multi-layered loss prevention strategies. The traditional coin-operated lock system uses a financial deposit to incentivize returning the cart. Many locations have shifted toward high-tech perimeter security systems installed directly into the store's paving. A specialized wheel snaps into a locked position the moment it crosses a yellow painted boundary line on the asphalt. This cross-section of a smart wheel shows the system in operation. An underground 8 kHz RF transmitter cable communicates with an internal receiver, instantly deploying a motor-driven mechanical brake arm. For carts that manage to bypass perimeter defenses, some stores employ GPS cellular tracking and hire third-party retrieval services to recover stranded assets from local neighborhoods. Modern carts operate within a high-tech security grid, built to ensure the store's capital investment remains on the property. The next phase of retail operations involves a transition to digitized smart carts. These units are equipped with large touchscreen displays and scanning interfaces mounted directly over the basket. These vehicles integrate new hardware, including built-in AI cameras, barcode scanners, and weight sensors that track every piece of inventory entering the basket. These features sync directly with the store's point-of-sale system, allowing shoppers to verify their totals and pay on the screen, skipping traditional registers entirely. Smart technology merges physical capacity with digital data, turning the vehicle into an autonomous checkout lane. The unit economics of a standard cart involve a manufacturing cost of $75 to $400 per unit. This is compounded by ongoing expenses for regular retrieval, sanitization, wheel replacement, and perimeter security. These overheads are balanced against the cart's ability to facilitate bulk item purchasing and family shopping. This equipment removes the physical barriers that would otherwise limit a customer's spending. By allowing for transactions that would be impossible with a hand-carried basket, the cart provides a massive return on its initial cost. The shopping cart remains the primary instrument for aligning customer comfort with profitability, moving millions of tons of goods through the global economy every day.